This is a wedge question from the 2008 mock paper. It's question 4. And in the question we're given this diagram here, and we're shown a wedge and with a pulley attached to the wedge, and going over the pulley we have a string attached to 2 masses, 5 kg resting on the wedge surface here, and a 2 kg mass hanging over the edge. We're also told that the tan of the angle A is 3/4, therefore we can draw this little triangle over here to work out the full trigonometry of that triangle. So if that's 4 and that's 3, by Pythagoras' theorem the hypotenuse must be 5. And so let's try and visualize what's happening here. Well, the 5 kg is heavier, so that should go down the plane here. We'll just call that the acceleration A, down the plane, which means the 2 kg is going to go up with an acceleration A. So let's just put that in there. It's going to go up with acceleration A. At the same time as the pulley system is moving on the string, the wedge moves underneath with its own acceleration F to the right. Now, first part of the question is to show the forces on each mass separately on a separate diagram. So let's take the 5 kg mass first, and let's think about the forces on that. 5 kg is going to have its own weight pulling down, 5g down this way. It's going to have a reaction force from the plane, and it's also going to have tension from the string here. So let's just put in that tension. And if we draw the full force diagram, you get this diagram here. So the 5 kg mass, 5g downwards is the weight, R is the reaction force, T is the force from the string. Next thing you have to do in a wedge question is to pick your x-axis and your y-axis, and your x-axis should always be along the plane for these masses. And once you got your x and y axis defined, then you got to look at your 3 forces and see if any of them need to be resolved according to the new x and y axis. So it looks like R and T are okay. They're already along x and y. So we have to resolve 5g. So bring that down here off the main diagram. The examiner doesn't like resolving forces on the original diagram, so you have to bring it down here. Bring down your 5g. By trigonometry, that's the angle A again. This is 5g cos A and 5g sin A. So there's the force diagram for the 5 kg mass. I would also put an acceleration diagram beside it separately, and I always like to emphasize the acceleration in a different color so that it's not mixed up with force and with force. This is a common mistake with students to mix up forces and acceleration in their equations, so I like to color code them, keep them separate. Okay, so let's look what's happening with acceleration then. Well, the 5 kg is going down the plane with this acceleration A, but at the same time the plane is moving underneath it in the direction to the right, so we show that with the acceleration F of the wedge. So the wedge's acceleration is F. The mass moves on the plane with acceleration A. So the actual acceleration is a combination of these two. And again, because we got an x and a y axis to think about, we have to resolve everything along those, whether it's forces or accelerations. So A is already okay, but F has to be resolved according to the new x and y like this. Again, that's the angle A in there also, it's the same angle as here. So we get F cos A and F sin A for the acceleration. That's the 5 kg done. Now we go to the 2 kg, which is touching off the side of the wedge, hanging over the edge from the pulley, over the pulley. And the forces on that would be its weight downwards again, 2g, the string, tension T, and the wedge pushing against it from the left. We call that force, force P. So there are 3 forces. And we can use the x-axis this time as our normal horizontal. It makes more sense because all the forces in the diagram are horizontal and vertical anyway. So there's x and there's y. And now moving to the acceleration, again use some kind of color coding to emphasize the accelerations can't be mixed up with forces. So I mean, this would accelerate. I mean, if the 5 kg is moving down the plane with acceleration a, if we go back to the original diagram, if this goes down with a, this must go up with a. So the 2 kg goes up with acceleration a, but again, don't forget at the same time the wedge is moving to the right with acceleration f. So it obviously pushes 2 kg. 2 kg must take on the same horizontal acceleration as the wedge because they're touching. So its acceleration is f. So there's your acceleration diagram for the 2 kg mass. And finally, we must do the forces on the wedge itself. Now, we have to be careful here again. The wedge itself, because the wedge is pushing the mass 5 kg. This is the 5 kg mass here. It pushes the 5 kg with a force R. So by Newton's third law, 5 kg must push back with an equal and opposite force R. Common mistake here is for people to put in actually the weight again. They put in the 5g downwards. That's wrong because this time that would be the force actually on the 5 kg. This time we're only interested in the forces on the wedge itself. So the weight 5 kg is not necessarily the weight that's actually on the wedge. By Newton's third law, if the wedge pushes the 5 kg with R, the 5 kg pushes back with R. So be careful there. So we've got R. Also, the same argument here applies for the 2 kg mass. And if the wedge pushes the 2 kg with a force P, well, the 2 kg pushes back with P as well. Let's make that a bit clearer there. Okay, other forces. Well, the wedge is on the ground, it's free to move, so the ground is pushing up with some reaction force as well. We call that N. And finally, one that you might forget easily when there's a pulley involved. The pulley is the tension on the string is kind of digging into the pulley, which digs into the corner of the wedge. So these two forces are actually felt by the wedge. These two tension forces on each side. They're both felt by the wedge separately. And lastly, of course, the wedge has acceleration f to the right. So put the acceleration again over here in a separate color as f. Now, once more, we have to do some resolving because it's again, you pick the x and y axis to make things easy for yourself. Technically, it can be in any direction, but we are going to always make life easy for ourselves. So most of the forces would be horizontal and vertical. So if we pick the odd one out, R and R here needs to be resolved. So we won't have to resolve that force R along x and y. And again, by the trigonometry, if that's A, that's 90 minus A, so that's A again. That's going to be R cos A and R sin A. And same with T. This T is okay, but this T up here needs to be resolved. And working out angles, this angle A is the same as this angle here, so this is A. So we've got T cos A and T sin A. And that's all the forces now resolved either along x or along y. So back to the original question, we've got all our resolving done, we've got all our forces, we've shown the force on each mass and on the wedge on separate diagrams, and we've put in accelerations as well. Now to calculate the acceleration of the wedge, calculate F. we've got to now go back to our diagrams and use our f equals ma in each situation to get simultaneous equations which involve f. And once we've got enough simultaneous equations, we can then solve for f. That's the method always in these questions. So we use f equals ma. So we use our force diagrams to get an f equals ma equation. We can get two for each diagram, one horizontal and one vertical. So once you've got your f equals ma equations, once you have enough of them with the unknown f, you can solve to get f. That's the idea. So let's go back and have a look at those. First diagram here. Well, let's look at the horizontal first. So let's look at r along x. And from the acceleration diagram, we can take it as it's moving down the plane. So if we apply f equals ma, we get the f from the force diagram, we get the acceleration from the acceleration diagram. So the overall force along x here is, well, we see just 5g sine a, 5g sine a in the forwards x direction, but in the minus x direction we've got t. So it's minus t is equal to mass by acceleration. The mass is 5 and the acceleration, be careful, is a in the forwards x direction minus f cos a in the minus x direction. And that's 5g times the sine of a. If we go back to our triangle, the sine of a is 3/5. So it's 5g into 3/5 minus t equals 5a minus 5f times the cos of a, which is 4/5. And that works out nicely for us because the 5's cancel. 3g minus t is equal to 5a minus 4f. So there's one equation in with f in it. The only trouble is we have two more unknowns, t and a, so we've got three unknowns altogether, which means we need at least two more equations to be able to solve for f. So we have to keep going. And you get the next equation by doing something similar for the for along y. And along y, right down here, f equals ma again. And if you look along y, if you just focus on what's happening in this direction only, and look at the acceleration, we see the only acceleration that's happening is actually down this way, f sine a, in the minus y direction. So the minus y direction is actually the direction it's moving in. So that's the forward direction. So the forward direction for force is 5g cos a. So we have 5g cos a is the forwards force, and we've got minus r is now in the minus direction, equals mass, which is 5 by the acceleration, which is f sine a. And that's going to be your second simultaneous equation, and you will get you get two more here, and you'll get two more for the wedge. And you very often you won't need all 6 equations. You just, if you can find, a shot will probably be to find the first 3 that will give you 3 unknowns, where f is one of those unknowns. But the basic idea will be the same to finish off the question. Just get a horizontal and vertical for here, using the two diagrams, and do the same for the wedge using the two diagrams, and you'll potentially have 6 equations, of which you'd only usually need 3 of them or so to solve for f.